everybody, my name is Sibel, and today we're going to be talking about Structure 3.1, the periodic table, classification of elements. First, let's start off with the history of the periodic table. The periodic table was created by a Russian scientist named Dmitry Mendeleev. This guy had no knowledge of the structure of the atom, but based off their characteristics, he was able to assign places to them by grouping elements with similar properties. Fun fact, when he first created the periodic table, there were still elements scientists hadn't discovered yet. So there were gaps in Dmitry's periodic table. He predicted that new elements would be discovered and fill in the gaps. He was absolutely right. Now let's talk about periods and groups of the periodic table. The elements of the periodic table are placed in order of increasing atomic number, which is denoted by Z. The atomic number of an element is equal to the number of protons in its nucleus. This here is an image of the periodic table. As you can see, we have periods, groups, and blocks. The periods are the horizontal rows, the groups are the vertical columns, and the blocks are the big chunks of things, elements, which are colored in the same color. Let's talk about the periods first. The periods are primarily characterized by elements that have the same number of occupied principal energy levels. What does that mean? So let's talk about lithium. The electron configuration of lithium is 1s, 2s1. This means that the coefficient of 2 over here is going to give us the period number. Let's try this for another element on period 2. Let's do nitrogen. Nitrogen's electron configuration is 1s2, 2s2, and 2p3. See how the valence electrons are again in the second principal energy level. That means that these two elements, lithium and nitrogen, are going to be in the same period because they have the same number of occupied principal energy levels. Now let's talk about the groups, which are the columns. The groups are going to be like this. They're going to go down. They're going to be vertical. Let's give examples. So we know that elements in the same group are going to have similar chemical and physical properties. Let's give an example. So group 18 elements, you've probably heard of this before, but they're called noble gases. They all exist as gases in room temperature, and they are all very reluctant to undergo chemical reactions. Now let's give another example. The group 1 elements are the alkali metals. They undergo chemical reactions readily. They each have 1 electron in their valence shell, and they have high metallic character, except for hydrogen. You have to be careful when you're talking about hydrogen because hydrogen is not an alkali metal. It's an exception. Now we can talk about the blocks. The blocks are going to be grouped using these colors. Let me just name these blocks real quick. This block is going to be the S block, this is the D block, this is the P block, and this is the F block. If you're thinking to yourself, how am I supposed to remember this? Well, just remember that. Let's draw the electron configuration of lithium one more time. 1s2, 2s1. Notice how it ends, the valence electron is in the s orbital. Let's try for something else. Let's do boron. We can do boron. Boron's going to be 5, so that's 1s2, 2s2, 2p1. Notice how the valence electron is in the p energy level. That's a dead giveaway of where it's supposed to be in the periodic table. One more thing worth noting is the metalloids. Metalloids, they're kind of in between metals and nonmetals. Physically, they look a lot like metals. And they kind of have similar physical properties. But chemically, they act more like nonmetals. The metalloids go in a ladder-like direction, starting with silicon, germanium, arsenic, antimony, tellurium, and polonium. These guys are the metalloids of the periodic table. Moving on to the properties of elements. So the properties we're going to be talking about are the atomic and ionic radii, electronegativity, ionization energy, and electron affinity. Let's begin with the atomic radius. So the atomic radius is measured as half of the distance between two neighboring nuclei. Let's draw what it looks like. This is a nucleus. This is another nucleus. This is going to be half the distance between two of them. So this is going to be R, this is going to be R, this is going to be 2R, and 2R divided by 2 is going to give us R. For many reasons, however, the distance from the nucleus to the outermost electrons of the atom can also be a definition of what the atomic radius is. Let's say the outermost electron is going to be over here. This is the distance. It's going to be R, and that is another way to measure atomic radius. So let's talk about the general trend of the atomic radius. I like to use something called the snowman model to help me figure out what the general trend of the atomic radius is going to be. So let's just draw a little snowman. It's got to be facing the right side, though. It's very important. It's going to get bigger as it goes down, and over here it's going to get smaller as it goes right. You can think of that as its carrot nose and that these circles as its body. So what does this say about atomic radii? So basically, if you think of this as the periodic table, that's a very roughly drawn periodic table, the atomic radius is going to increase, as you can see over here, as you go down, and decrease as you go to the left. Right, like this. So let me just write it down. Increase as you go down, and decrease as you go to the right. So why is that? Let's talk about the easier one, the increase as it goes down. Like we mentioned before, as we go down, as we progress in periods, the number of occupied principal energy levels increases. Oops. This means that, let's give an example from the periodic table. If we were to compare lithium and potassium, you would realize that lithium has a much smaller atomic radius. Because the valence electrons in the lithium atom are going to be in the 2s sublevel, and the valence electrons in the potassium atom are going to be in the 4s sublevel. The 4s has a higher coefficient, so it's going to be further away from the nucleus, and hence it's going to have a bigger atomic radius. Now let's talk about the more tricky part, the decrease in the atomic radius when you go to the right. So we can't talk about the occupied principal energy levels when we're talking about this, because as you know that elements in the same period, they're going to have the same occupied principal energy levels. So that's not going to work. However, like we mentioned before, the elements are ordered in a sense that when you go to the right, the number of protons increases, which is going to be the atomic number. If the number of protons increases, the nucleus is going to have a higher pull on the valence electrons, because the charge density of the nucleus is going to be more positive. And so it's going to attract electrons to the core, which is going to be the nucleus, more. So to summarize, the attraction between the nucleus and the outer electrons increases as the nuclear charge increases, so there's a general decrease in atomic radius across a period. Let's move on to the ionic radius. So the ionic radius is pretty similar to the atomic radius, except this time you got to use ions. So you can use the sodium ion, but not the sodium atom, because that would be atomic radius. Right now we're going to focus on ions and their radius. So you can use the same snowman model here. As you go down, the number of occupied principal energy levels increases, and as you go to the right, the attraction between the nucleus and the electrons, the electrostatic attraction between them, it's going to increase, so that protons are going to have a higher pull on the electrons, accounting for a smaller ionic radius. So let's look at these ionic radius examples. This is their atomic radius and this is their ionic radius. Let's look at sodium, magnesium, aluminium. Okay, that's a predictable trend of the increased proton number and therefore the higher electrostatic attraction between the valence electrons and the nucleus. However, when we get to silicon, there is a discrepancy. Over here it says 40, but over here it says 271. That is a huge jump in ionic radius. And look at what it depends on, whether the charge is negative or positive. Let's talk about it. These electrons are going to repel each other, just like what I said over here. When you introduce new electrons to an atom or an ion, these electrons are going to move farther away from each other because of the electrostatic repulsion between them. And that's how you have the huge jump between the silicon ions. So positive ions are smaller than their parent atoms. This is because of the loss of the outer energy level. So when we're talking about, say, sodium, the sodium is going to be in a +1 charge, so which means it's going to give away 1 electron and it's going to have lesser occupied principal energy levels, accounting for a smaller ionic radius. So negative ions are larger than their parent atoms. This is because when you add another electron to an atom, making it an ion, these electrons are going to repel each other and they're going to move farther apart, which is going to make the ionic radius bigger. The ionic radii decrease from groups 1 to 4 for positive ions due to the increase in nuclear charge. As we talked about this previously, the increase in nuclear charge accounts for electrons moving closer to the nucleus. And now let's talk about the discrepancy of silicon. The ionic radii decrease from groups 1 to 14 for the negative ions due to the increase in nuclear charge across the period. Let's go up here and talk about silicon. So over here, I have the electron configuration of silicon. If we have 2 ions for silicon, let's talk about the positive ion first. So for the positive ion, we're going to have to remove these electrons and look at what we have. We have only 2 occupied principal energy levels. So this one is going to be smaller. Now let's talk about the larger one. The negative ion. So let's add 4 electrons over here. We know that the p orbital can hold up to 6 electrons, so that's going to be 6. Now for the ionization energies. The ionization energy is basically a measure of the attraction between the nucleus and the outer electrons. Over here we have a graph depicting the ionization energies of the first 20 elements. So there are 2 general trends you can see from figure 2. So I'm going to draw what the ionization energy trend basically looks like in the periodic table. It increases like this. So when you go to the right, it increases. And when you go down, it decreases. So basically, this is increases. So the ionization energy increases when you go right because of the increase in effective nuclear charge. So because the shielding effect is pretty constant, the attraction between the more protons as you move right and the number of protons increases and the electrons is going to be higher. So the pull of the nucleus on the electrons is also going to be higher, which makes electrons in the outer energy levels more difficult to remove. And the other trend is it decreasing when you go down and increasing as you go up. So The reason why it decreases as you go down is because something called the shielding effect. So the effective nuclear charge is the net attraction between the protons and the electrons. And you may say, what do you mean net? What does that mean? Is there something preventing the protons from attracting the electrons completely? Well, if you're asking that, then you're absolutely right, because the shielding effect is what does this. So the electrons in an inner energy level repel others in outer. So electrons in an So the electrons in an inner energy level repel others in outer energy levels. Let's draw a little figure. These are going to be electrons in the inner energy levels, and these are going to be the electrons in the outer energy levels. So obviously we have repulsion between these two electrons. So these electrons are going to want to go farther away. So if they're farther away, then the attraction the protons have on electrons is going to be less attraction. So it's going to be easier to remove these electrons. Given that the definition for the ionization energy is the amount of energy required to remove 1 mole of electrons from 1 mole of gaseous atoms in their ground state, this supports the idea that ionization energy increases as you move over to the noble gases, because they have a strong attraction on their valence electrons, which makes them reluctant to undergo chemical reactions. Moving on to the electron affinity. So the definition of an electron affinity is the energy change that occurs when 1 mole of electrons is added to 1 mole of gaseous atoms to form 1 mole of gaseous ions. So let's look at this equation over here. We have 1 mole of gaseous atoms in the gas state. If you add 1 mole of electrons, you're going to get 1 mole of gaseous anions. And since this energy this process generally gives out energy, it's called exothermic. And the general trend is that it increases across a period and decreases down. We have another exception in chemistry. So this exception is about the first and second electron affinity of oxygen. So as you know, the first electron affinity is generally going to be exothermic, which releases energy. Why? Because the electron, the oxygen atom, really wants an electron. It wants to form a stable octet, and therefore needs an electron to do so. But the second electron affinity is going to be endothermic, which requires energy. Why? Because when you have an oxygen ion, an anion, if you give another electron, these electrons are going to repel each other, especially with the one you recently added. So this is going to require energy because this is not its most stable state. And that's why the second electron affinity for oxygen is endothermic. Now we're moving on to electronegativity. So the general trend in electronegativity is that it increases when you go right across a period and decreases when you go down a group. So the electronegativity is a measure of the ability of an atom to attract electrons in a covalent bond, which is a bonding electron. Recall what a water molecule looks like. We have an oxygen, we have an hydrogen, we have an hydrogen. Oxygen has a higher electronegativity, so the electrons are going to stay around the oxygen more, which makes it partially negative, and the hydrogen is partially positive. The electronegativity of an element accounts for an increase in nuclear charge. As you can see, when you go right, the increase in nuclear charge helps the protons attract electrons more. And when you go down, the electrons are furthest from the nucleus, so there is reduced attraction. When you're further away from the protons, the electrons don't really have as powerful as an attraction between these guys. Structure 3.1.4, periodicity and reactivity. So, group 18, as we talked about, are the noble gases. Noble gases have a complete octet. So the reactivity of elements in other groups can be explained by their unstable, incomplete electron energy levels. They lose or gain electrons to achieve the electron configuration of the nearest noble gas. The noble gases, every single electron that forms, every single element that forms a complete octet wants to have the electron configuration of the nearest noble gas. This also explains why noble gases are hesitant to undergo chemical reactions. They already have a pretty stable and complete electron energy level. Now we're moving on to the group 1 alkali metals. So the physical properties of the alkali metals, this I have to mention, you cannot include hydrogen here. Hydrogen is a nonmetal, first of all, and it does not share the same characteristics of the alkali metals. So the physical properties of these guys are that they're good conductors of electricity and heat, just like any other metal. Most other metals, they have low densities, which is unique. They have shiny gray surfaces when freshly cut with a knife. This is also pretty unique because you can freshly cut them with a knife, which sounds very interesting, but it's true. So the chemical properties are that they're very reactive metals. This means they have high metallic character. What is metallic character? It's the tendency to give away their valence electrons to form cations. They form ionic compounds with nonmetals. So let's talk about their reactions with water. We're going to talk about lithium, sodium, and potassium over here. So lithium basically floats on water and reacts pretty slowly. It releases hydrogen but keeps its shape. By hydrogen, it means hydrogen gas, and it retains its shape pretty well. Let's draw the chemical equation of this. So we have lithium and H2O. This is going to release lithium hydroxide, which creates a base, and hydrogen gas. Yes, so it's pretty tame when compared to the other alkali metals reactions with water, but it's important to note that it creates a base and it releases hydrogen gas. Sodium reacts with water and releases hydrogen vigorously. The heat produced is sufficient to melt the unreacted metal, which forms into a small ball and moves around the water surface excitedly. So let's write down the equation for this. When it meets water, it's going to be sodium hydroxide and H2 gas. Last but not least, we have potassium. So potassium reacts very vigorously with water to produce sufficient heat to ignite the hydrogen produced. It produces a lilac flame and moves excitedly on the water surface, turning into a little ball. So let's write down the chemical equation of potassium with water. It's going to produce potassium hydroxide and H2, which is ignited and creates a lilac flame. Let's balance the chemical equation, and notice how I'm basically copying and pasting the same coefficients in the same way. That is because they're in the same group. They all end off, all of their valence electrons in the s orbital. So this one has the 2s orbital, this one has the 3s orbital, and this one has the 4s orbital for its valence electrons. That's why I can use the same exact thing and copy paste it. Also, it's important to note that these guys produce, the alkali metals produce bases when reacted with water because of their OH groups when they react with water and their products. These guys, the metallic oxides can dissociate in water and produce OH groups, negatively charged OH groups. Group 17, the halogens. So the halogens are generally exist as diatomic molecules. Why is that? Let's give an example. Chlorine. As you probably know, chlorine only exists as Cl2, never as Cl in nature. This is because of its... You will learn about this in more detail when you learn about the covalent bond and the Lewis model. But for now, just know that these halogens always exist as diatomic molecules. So their physical properties are that they are colored. This is going to be important in the future, right over here. And they show a gradual change from gases to liquid and solids at room temperature. This is accounted by van der Waals forces, which you will learn about later on. So the chemical properties are that they are very reactive nonmetals. Their reactivity decreases down the group, and they form ionic compounds with metals and covalent compounds with other nonmetals. As you can see, they are colored compounds. Iodine looks kind of purplish, bromine looks brown, and chlorine looks yellow. So the reason why these the reason why these elements are very reactive nonmetals is because of their electron configuration, of course, and their readiness to accept electrons. The nuclei have a very high effective charge of approximately 7+, so they exert a strong pull on any electron from other atom. So you can think of these elements as very selfish, and they want all the electrons around them for themselves, especially chlorine and especially fluorine because it's more electronegative, but it's not illustrated. Okay. And especially for fluorine because of its high electronegativity. Now let's learn about displacement reactions. Displacement reactions are all about electronegativity. Let's take a look at this reaction. A chlorine nucleus has a stronger attraction for an electron than a bromine nucleus. So what does that mean? Right now, chlorine has an oxidation state of 0, and bromine has an oxidation state of -1. You will learn about oxidation states in a bit. But chlorine has a higher attraction on a bonding pair of electrons, which means it has a higher electronegativity. It is more inclined to become negative than bromine because electronegativity increases as you go up, and bromine is way down. So it basically steals bromine's electron, and it's basically displaced with bromine. Bromine has an oxidation state of 0 now, and chlorine has an oxidation state of -1. This can also be seen with ions. Bromine has a negative oxidation state, chlorine has 0, so chlorine is going to take away the electron from bromine, the bromide ion, and it's going to become a chloride ion, and bromine is going to have an oxidation state of 0. Do you remember when we talked about color? Well, it's important to note that ions of halogens, which are group 17 elements, have no color. So you can basically infer what the color change here is going to be. This has no color, and this has color. So at first it's going to be yellow, and then this is going to have no color, and this is going to have color, and then you're going to be able to see brown. Now, do you remember recall that color change is a telltale sign of a chemical reaction? Well, you have that right over here. So over here, I have the inputs of a chemical reaction. Can you tell me what the products are going to be of this chemical reaction? You can pause the video to answer. If you answered no reaction, you would be correct. Let's look at it. So let's assign electronegativity values. Fluorine is going to be -1 and iodine is going to be 0. Recall that fluorine is more electronegative than iodine. And that fluorine is the most electronegative element there is. So fluorine is going to be more inclined to have a negative oxidation state, and iodine is sadly not going to be able to attract the electron. So no reaction happens. Let's move on to the halides. Halides are basically ions of halogens. This could be the fluoride ion, the iodide ion, and so on. So halogens form insoluble salts with silver, which is Ag. Adding a solution containing the halide solution. Adding a solution containing the halide to a solution containing silver ions produces a precipitate. A precipitate is basically, in a liquid, it's the solid that sinks to the bottom. It's insoluble, it's salt, and it sinks to the bottom, and it's useful in identifying the halide ion. As you can see over here from this reaction, the silver ion and the fluorine ion produces a silver fluoride ion, salt. So let's look at the colors of these. As you can see with the halides, which is group 17, as you move down, halides are going to become more yellow. So let's take a look at it. So silver chloride, this is silver chloride, this is silver bromide, and this is silver iodide. As you can see, as you go down in the halides group, it's going to get more and more yellow. So this is like a purplish color. This is white, and this is yellow. Moving on to the metal and nonmetal oxides. So the bonding of period 3 oxides. The transition from metallic to nonmetallic character is illustrated by the bonding of period 3 oxides. Since oxygen is a nonmetal, when you have ionic characters, you have metals and nonmetals bonded together. And when you have covalent molecules, you have nonmetals bonded with nonmetals. An interesting exception is the oxide of silicon. Recall that silicon is a metalloid. It's kind of in between a metal and a nonmetal. It produces a giant covalent structure. Let's remember what structures ionic and covalent substances produce. Ionic structures have a lattice structure, which is a giant structure, and covalent molecules have a molecular structure. On the other hand, silicon, a metalloid, has a giant covalent structure. This means that there's repeating patterns, but also covalent bonding. The ionic character of a compound depends on the difference of electronegativity values. So, as you go right in the periodic table, the ionic character of the oxides decreases. Because, as you go right, the electronegativity increases, so the difference between the electronegativities is going to decrease. Let's take a look at this graph, this table. As you can see, we're going right in the period 3 oxides. Let's take a look at the ionic character. So we have electrical conductivity in molten state. This being high is a telltale sign of ionic character. Its structure is going to be giant ionic, which is another sign of ionic character, and its oxidation numbers are pretty low. And when you move to the right, it's going to go from giant covalent to molecular covalent, which means a low electronegativity difference. because both of the electronegativities of the elements over here are pretty high, so the difference is going to be low. We can move on to the acid-base character of the period 3 oxides. So, generally, what do you see over here based off the bonding? As you can see, the more ionic character displayed makes a substance more basic, and more covalent makes it more acidic. What about aluminium oxide? What is amphoteric? We're going to talk about that in a bit. So basic oxides dissolve in water to form alkaline solutions, which has a pH greater than 7, owing to the presence of hydroxide ions. Hydroxide ions are OH ions, and if there's a lot of this, more than H plus ions, it's going to be basic. Alkaline. As you can see, when a sodium oxide mixes with water, it produces sodium hydroxide, which dissolves in water to produce an alkaline solution. Moving on to nonmetallic oxides, these are going to be acidic. So, as you can see from an example here, we have a nonmetallic oxide of carbon and oxygen, and when you mix it with water, you get a weak acid. As you go... Now let's talk about sulfuric acid. Sulfuric acid, once again, when you mix it with water, this time you get a strong acid. And amphoteric oxides. So these oxides can act as a base or acid, depending on what they're mixed with. An example is aluminium oxide. You don't have to memorize these chemical equations, but just know that they can act as a base or acid. Over here, it behaves as a base when it reacts with sulfuric acid. And because of the neutralization reaction here. If you mix a base and an acid, it's going to neutralize. And it behaves as an acid when it reacts with alkalis, such as sodium hydroxide. Over here, you can see another neutralization reaction, an acid-base reaction. It's behaving as an acid when mixed with sodium hydroxide. Acid rain and acid deposition are produced by nonmetal oxides, which are the acidic oxides. So, under normal circumstances, all rainwater has dissolved carbon dioxide, so a pH of 6.5 is normal. The problem is not CO2, but these two guys, sulfur monoxide and nitrogen monoxide. These are the two oxides that decrease rainwater's pH into a state that is dangerous, which is below 5.6. Let's look at the examples. Over here, sulfur, which comes from fossil fuels, reacts with oxygen in the air and produces sulfur dioxide. This can later on mix with water to produce sulfuric 4 acid, which is over here. And it can even oxidize further with oxygen, producing sulfur trioxide, and reacting with water, producing sulfuric 6 acid, which is even stronger than sulfuric 4 acid. Nitrogen oxides produce acid rain also. Nitrogen comes from internal combustion engines. When it reacts with oxygen in the air, it produces nitrogen monoxide. When it reacts further with oxygen, it produces nitrogen dioxide. And this is another alternate pathway for nitrogen dioxide. And when it mixes with water, it's going to produce these two nitric acids. This is an alternate reaction for nitric 5 acid. And yeah, these two, sulfur and nitrogen oxides, are the causes of pH being too low in rainwater and eventually causing ocean acidification. Ocean acidification occurs as carbon dioxide dissolves in the oceans. So when carbon dioxide dissolves in water, it's going to produce carbonic acid over here. It's a weak acid, as described by this arrow. Carbonic acids then reacts to form hydrogen carbonates or carbonates, which is over here. Now let's talk about oxidation states, which is one of my favorite topics. So the oxidation state is a number assigned to an atom to show the number of electrons transferred in forming a bond. What does that mean? It is the charge that the atom would have if the compound were composed of ions. So it's basically kind of like an ionic charge, except it's different and you can assign it to nonmetals. Oxidation. We have to remember that oxidation can involve elements other than oxygen. Even though it sounds like it can only apply for oxygen, oxidation can happen to any element. Let's see. When magnesium reacts with oxygen, it is oxidized and forms the ionic compound magnesium oxide. Let's assign oxidation states. So, the oxidation state of an uncharged element is always going to be 0, as seen over here. However, now we have a compound, oxygen usually has an oxidation state of -2, and magnesium usually has an oxidation state of +2. This is because magnesium is in group 2 and has 2 valence electrons in its outer shell. So as you can see, oxidation is an increase in oxidation state. Let's see. So, magnesium used to have an oxidation state of 0, but now it has a oxidation state of 2. So we can say that magnesium was oxidized. And oxygen had an oxidation state of 0, and now has an oxidation state of -2, which means it was reduced. As you can see from this example, magnesium over here is oxidized again, even though there's no oxygen. You can remember oxidation as the addition of oxygen, the removal of hydrogen, an electron loss, or an increase in oxidation state, which I think personally is the easiest to remember. Oxidation states are a measure of how electrons are distributed. Let's talk about chlorine, the diatomic molecule. So chlorine is going to have an oxidation state of 0 because electrons are evenly distributed between the 2 chlorine atoms. Electrons evenly distributed. Now let's talk about sodium chloride. Chlorine is going to have an oxidation state of -1, and sodium is going to have an oxidation state of +1. This is because when an atom, which is sodium, is bonded to a more electronegative atom, it loses some control over its electrons and has a positive oxidation state. So here are some rules to assign to oxidation states. Number 1, atoms in a free, uncombined element have an oxidation state of 0. Because it doesn't lose any control over its electrons, it's going to have an oxidation state of 0. In simple ions, the oxidation state is the same as the charge of the ion. Let's talk about magnesium ion. So over here we have the charge of the ion, and if we needed to write down the oxidation state, that'd be +2. Remember that 2 plus is not equal to plus 2, or vice versa. This describes the oxidation state. And this describes the charge. We have to be very careful when writing these down because these two are completely different, and the IB is very strict about the differences between the two. The oxidation state of all atoms in a neutral uncharged compound must add up to 0. Let's see. The sum of the oxidation state in sulfuric acid is going to be 0 because hydrogen is going to have an oxidation state of +1. Oxygen is going to have an oxidation state of -2. And sulfur, let's see what sulfur is. So in cases like this, we're going to have to use the more commonly So in cases like these, oxygen is almost always going to be -2 oxidation state-wise, and hydrogen is almost always going to be +1. So using these, we can infer the oxidation state of sulfur. Let's see. So hydrogen, we have 2 hydrogens, so it's going to be +2, and then we have 4 oxygens, so that's going to be -2 times 4, and we have 1 sulfur, so we're going to do a +S, which must be equal to 0, based on our rule. It must add up to 0. So let's see. This is going to be -8 plus 2 plus S is going to be 0, which means -6 plus S is going to be 0, which means if we add 6 to both sides, S is going to be +6. So sulfur is going to be +6. The oxidation states of all the atoms in a polyatomic ion must add up to the charge of the ion. So, as you can see, the charge of the ion is going to be equal to the oxidation state of the ion. The usual oxidation state for an element in a compound is the same as the charge on its most common ion. As you can see, group 1 metals are +1, which is sodium is always going to be +1, and group 2 metals are going to be +2, which is magnesium. As an example, it's going to be +2. Fluorine has an oxidation state of -1 in all of its compounds as it is the most electronegative element. It's going to have control over the electrons. So no matter what you do with fluorine, it's always going to be -1. Oxygen has an oxidation state of -2 for most of the time, except when it forms peroxides such as H2O2, where it is -1. Let's draw it down. We have 2 hydrogens, which is going to be 2. This is going to have an oxidation state of 0. So let's do 2 times let's do 2 times -O equals 0. So 2 times O is going to be equal to -2. O is going to be equal to -1. As you can see, oxygen has an oxidation state of -1 here. And when bonded to fluorine, it is positive as it is less electronegative than fluorine. We just talked about fluorine being the most electronegative element, so it's going to be more inclined to have a negative charge. And obviously, because this has to have a charge of 0, oxygen has to have a positive oxidation state. Chlorine has an oxidation state of -1, except when bonded to the more electronegative F and O. Fluorine and oxygen. It can be a +1 oxidation state, +1 oxidation state, or +7 even in when bonded to oxygen. Hydrogen has an oxidation state of +1, except when bonded to group 1 and group 2 metals when it forms ionic hydrides. As you can see here, since sodium has to be 1+ always, hydrogen has to be -1, and magnesium has to be +2 always. There's 2 hydrogens, so each hydrogen is going to be -1. These are the ligands, and these are only an HL topic. So the oxidation state of a transition metal, which is like titanium, or copper, and a complex ion can be worked out from the charge on the ligands. So the common ligands include H2O, NH3, Cl, Cn, and OH. Systematic names of compounds use oxidation numbers. So let's talk about sulfuric acid. Since sulfur can have a varying oxidation state, we go off of that to assign names. As you can see, both are sulfuric acid, as you can see, both are sulfuric acid, but they have slightly different conformations. So let's talk about it. Let's talk about the oxidation state of sulfur. So H is going to be positive, so that's going to be +2. Oxygen is -2, so multiply that by 4 and you get -8. Plus sulfur is going to be 0, and sulfur is going to be +6. So we're going to call that sulfuric 6 in Roman numerals acid. Now let's talk about this one. As you know, hydrogen is going to be +1, multiply that by 2 is going to be +2. Oxygen is going to be -2 because it's not bonded to fluorine, so it's going to be -2 times 3, which is -6, plus sulfur, and that's going to give 0, and sulfur must be +4. So this is going to be sulfuric 4 acid in Roman numerals.